Awesome. Hey, everybody. My name is Lucas Hampel, soon to be MSc of Physiotherapy, presently a student physio working for Clearwater Physical Therapy in Vernon and Fort McMurray, technically via telehealth from Brunel University, London. Thanks for joining us. This is the second lecture this week on the biology of pain. Last week we talked kind of broadly about a variety of topics. This week we're going to delve a little bit more into kind of the physiology, some of the anatomy, and a little bit of the cellular structure of pain and our biology in general. So let's get started. Quick overview just to kind of check things out, know where we're going throughout this little lecture today. Come on, slides, let's work. There we go. We're going to start off really simply. We're going to talk about what a neuron is and what detection really means at the very small cellular level. The neuron itself is an important structure that we need to understand in order to contextualize the nervous system in general. We're then going to touch on aspects of where this information goes, the stuff that is detected by those receptors we talked about last week, and how that information is conducted through neurons to our spinal cord and our brain. We're also going to touch on these aspects of central modulation of information and these ideas of neuroplasticity and this concept called the sensory homunculus, which is a little bit of a weird one. We'll kind of elaborate on it and how it relates to this whole paradigm. Which leads us into that next topic. How does the nervous system and these neurons and this physiology respond to pain? We'll talk about unhelpful adaptations, different things that happen peripherally, kind of in our limbs and in those nerves outside of our central nervous system, and also centrally. So those areas of the spinal cord and the brain, and how they change physiologically to adapt to different sensations, such as pain. We'll also talk about this a little bit about training the nervous system and different ways that we can use exercise or movement or mental exercises even, or even just rest, to mitigate pain or change our pain perception. Finally, I'm going to end off a little 5-minute little stint. Feel free to stay in if you want. If you don't, that's okay. I'm going to do a little bit of a mindfulness practice, something as a thought experiment exercise you can use to start disengaging that pain perception pathway and starting to kind of engage back with what you're feeling and how you can create that separation to use neuroplasticity and mitigate pain. So let's start with the neuron, or no, pardon me. Let's start with a quick review of what pain is, or what it's defined as. Pain, as defined by the International Association for the Study of Pain, is an unpleasant sensory and/or emotional experience associated with, or resembling that associated with, actual or potential tissue damage. It's a lot of words to say pain is unpleasant. It can be related to an injury, or it can be related to something unrelated to an injury, some sort of centralization or an emotional pain that is projected into the body to tell it that there is potential tissue damage or actual tissue damage. There's also these two other concepts that are important, acute versus persistent pain. We touched on them last week as a brief review. Acute pain is usually related to an injury. It lasts about 3 months or so, usually less. Versus persistent pain, which lasts greater than 3 months, and usually there's no associated tissue injury anymore. So those are kind of the two big concepts or big pieces that we want to be cognizant of when we're discussing this idea of the nervous system and how it changes and what it does. So let's get on to that next aspect, the neuron. The neurons are the fundamental building blocks of the nervous system. They are individual cells that conduct information from one to another. They connect to one another via synapses. So in the next slide, we'll have a little bit of a stylized version of a neuron. I'll kind of discuss our way through it as we're there. This information is conducted along specialized structures called axons or dendrites, depending on the structure itself or where the information is coming from. And neurons actually act as mini integrating centers. So they relay information or relay inputs from a lot of different other neurons' synapses, and then eventually conduct a signal if there's enough input from those areas. Nerves, as we understand them, are bundles of these axons or conducting structures from neurons that send information to or from the central nervous system to other areas of the body or the brain or the spinal cord. Again, really quick and dirty kind of version of what a neuron is. Let's take a peek at them. This is my fantastically simplified functional neuron unit. So on the left here, we have the cell body. This is kind of that general integrating center. It's where the genetic information is stored for the individual cell. It is also where the information from other neurons is collected and then eventually sent out as a signal. These projections, like star-like little projections, are called dendrites. They're a receptor structure that will synapse with another neuron and either collect information to increase the likelihood of a signal being produced, or decrease the likelihood of a signal being produced. If such a signal is stimulated through this cell body region, it will conduct down this long structure here called an axon. The axon essentially acts as a long signaling cable to conduct information to the axon terminus. This is also the same region where a synapse is. This axon terminus will connect to dendrites or the cell body of an adjacent neuron, or a neuron in the vicinity, or multiple neurons, because multiple axon termini can exist, and conduct that information forward. The myelin sheath is a fun little structure that helps to facilitate this process. The myelin sheath is actually wrapped sets of cells that essentially act as insulation along the axon, increasing conduction efficiency and allowing for signals to be produced and maintained faster along these axons. It's important to have this myelin sheath along our axons in order to allow for efficient and rapid signaling from one part of the body to the next, so we can respond to things quickly and in a protective and timely manner. So that's a neuron, very quick and dirty, very minimal. This is a scanning electron microscope picture. That picture that I offered earlier is very simplified. Neurons are messy. Neurons are very complicated. They can have multiple projections connecting to many other neurons in the same space. Here in this picture, you have one large neuron with a large axon right here, and all these other small fibers could be a mixture of axons or dendrites. It's a motley mess. Typically in our bodies, they're a little bit more clustered and organized, such that these long axon pieces are all connected and continuous, following the similar path along to connect to another neuron or to connect to the central nervous system. This here is just an example just to show you how complex this can be. We're talking about a very simplified version here. Continuing forward, we're going to talk about this information conduction. So let's say you pinprick a finger and you stab it, and there's a little bit of a pain sensation, or a threat of pain sensation created here. This could be damage to the area. This could be just a touch sensation. This could be that general little poking sensation. Let's go. This information is in the peripheral nervous system, the nerves and axons that conduct information from our periphery, our hands, our feet, our limbs, our torso, from those areas, conducting it and relaying it through axons or dendrites, depending on the structure, to our spinal cord, which is part of the central nervous system. This central nervous system area will interpret and evaluate the sensation. Both the spinal cord itself, which also acts as a conductor, and the brain can change the signaling intensity even after we've felt it as a sensation in the periphery, slightly increasing or decreasing the importance of that perceived sensation. To give an example of this, a simple anecdote, you place your hand on a countertop or place your hand on a countertop thinking it's a countertop, and instead it's the stovetop burner. Rapidly, the sensation that is detected in our hand is a lot of heat. That information is quickly conducted along an axon all the way through the peripheral nervous system to the central nervous system. Now, if it was just warm, our body would probably be okay with leaving it there for a half second, but because it's such a high heat, the central nervous system recognizes that structure, or recognizes that, and increases the signal response and allows you to, as a reflex, pull the hand off of that heated structure. Quick and simple there. Information, once it's reached the central nervous system, doesn't just end there. It is conducted through numerous areas within the brain. We have different regions that help to process different types of information. It contextualizes it. It colors the sensation that we felt to create a perception. This can be a perception of a pleasant sensation. This could be unpleasant. This could be the perception of pain. The coloring of it is based on our thoughts, our feelings, and our emotions, and even our understanding of what we just did to ourselves, which will change and contextualize that pain. An important aspect of this whole brain processing area is the somatosensory cortex. This is a key region, just kind of posterior to the midline of our skull, that allows us to map where sensations are felt. Going to go through a couple figures here. The first one is going to be that kind of cross section. So imagine that someone's chopped your head in half, perpendicular or parallel to your face. So this is the slice of the brain, the sensory homunculus, so to speak. As you can see, it's a little bit of a weird structure. These are the different areas along which the brain itself maps our sensations that we feel in our body so we can become aware of them. The brain essentially is in a big black box. So in order to understand where things are, it just has to have a visual or a virtual image of itself, an image of the body that it is housing. By extension, this sensory homunculus reflects the relative importance of different areas of our body. As you can see here, the hands are very large, as is the face and the mouth. This is reflective of the fact that our hands are very important tools. We need to be very precise with our ability to feel different areas. So our brain and our nervous system maps a lot of information from our hands to those regions. In the same way that our face is very important, and our mouth and things like that, because we require those structures to very precisely move and feel such that we can create sounds and make language and consume food and move food around in our mouth and so forth. To take this and move it forward, we have a fun little caricature people have made, a little sculpture. It's called the sensory homunculus. This is like the little man idea of what this would look like, what we look like in our own heads embodied. This is the derpy little sensory homunculus. He is quite a character. As you can see, it's that same kind of reflection of that importance of mapping. So you have the hands are very important, the mouth and the lips are very important. You can see the eyes and the ears, other sensory structures that provide a lot of information from our bodies to ourselves, so we know where we are in space and know how to use the structures that we have. So, long story short with these guys, our sensory homunculus is a virtual image of what our brain perceives our body to be, okay? Neuroplasticity is this concept related to this, and it can be related to a variety of things. Broadly speaking, when we learn, these neurons and connectivities in the brain areas will change. Neural connectivity can improve information conduction, and even the insulation, that myelin sheath, can actually become a little bit thicker, allowing the conduction along those signaling wires to become faster. This is adaptive usually. It allows us to learn new skills, it allows us to remember facts, it allows us to remember responses to things, previous experiences, and so forth. But what happens when we are affected by pain in the context of neuroplasticity, and especially in the context of persistent pain? A number of things can actually happen. We'll start on the small scale. So neurons, after you've been injured, will cause a variety of things. There can be damage to the myelin itself, that little sheath, that insulating thing that covers the cable that connects to the next neuron. This sheath can sometimes be removed. When that sheath is removed, it actually causes a phenomenon where sometimes new receptors are inserted into the axon, that conducting wire, which usually doesn't produce information, it just sends information. These new little receptors will cause significant changes to what we feel in those areas. Another thing that can occur when we respond to stimuli, or we are persistently feeling a sensation, is the myelin can instead be reinforced, which usually as a learning tool and neuroplastic tool is helpful because it improves our efficiency of finding that information. But here it can do the opposite. It improves the efficiency of sending a particular type of information, that of nociception, that threat of damage, to our brain, which can be interpreted in different ways. Usually, if we're talking about persistent pain, it is experienced as pain. So to come back to that neuron figure, we have this original neuron, this guy, sometimes a little bit dysfunctional. Cell body, dendrites, just to review, those are usually the integrating centers that send the signal down the axon to the next cell at the axon terminus and the synapse. What happens sometimes is our myelin sheath can become damaged. And when that myelin sheath becomes damaged, our bodies really like to fill in those spaces. Usually, eventually we'll refill it with myelin, but sometimes if the damage is large enough, or if we maintain a stress state or constant inflammation, sometimes what can happen is just along the middle of this axon, we can have new little receptors, those little hooks on that edge. Those receptors will create or respond to new stimuli, new signals. This may be pressure, this may be temperature. It doesn't matter what it is now sending a signal that is not actually dependent on the information being collected and processed from the neuron's body. This information then is conducted down in the very same way that it usually would be, but it may no longer be reflective of what's actually happening at the tissues these neurons are connected to. So to give an example, let's say you cut yourself weeks ago, but in the kind of interim time, you were rubbing it, you were worried about it, you were anxious about it, and the body hasn't actually effectively recovered the nerves and protected those axons with the sheath again. At this point, the cut has healed, the scar is the tissue is scarred, but for some reason, your body is still feeling like there is pain and soreness in that area. That can be part of this microscale physiological change wherein the nerve itself is actually conducting more information to the brain, despite the tissues being functional. Alternately, we have something that comes back to the kind of more macro scale part of the nervous system, that sensory homunculus and those kind of general regions, as well as some bits of habituation that can occur. Let's talk about our motor homunculus again, or sensory homunculus, pardon me. What happens with the sensory homunculus is now that if you're in a persistent pain state, our body becomes constantly aware of an area. By neuroplasticity, that change of the nervous system to improve efficiency of skills or sensations as we feel them, we become more aware of an area. So let's say, in this context, we've damaged a hand, we've hurt a finger, we've hurt our palm, we've hurt our wrist, whatever it might be, and it isn't getting better. We're still using the wrist, it's still feeling like it's not healing, we're stressed about it, we're worried about it, we're not sure if we did more damage than we think, we're uncertain about whether we should be moving it, it's becoming weaker, all these different pieces are occurring. But there's so much information and so much information being processed in our brains about what our hand is doing all the time. What this means is that we are teaching our brain, we're using that neuroplastic principle to become more aware of that hand all the time. So what actually happens physiologically is that area expands in the somatosensory cortex. It takes up more of that real estate in the brain to become constantly aware of that hand. And it's not, you'd think that would be useful, we're more aware of it, we're more capable of differentiating things, but it doesn't just broadly improve the signaling of everything, it improves the signaling of what we think about or what we're aware of. And in the context of persistent pain, this will be nociception, and by extension, how we color that nociception into pain. So we are more aware of our hand, we're more aware of where it is in space in the context of I could injure it if I move it here, or if I'm moving it, maybe that sensation is actually going to be painful and now I feel this. It's almost like a top-down approach where our central nervous system is actually facilitating that pain response in that part of the body. But another thing happens too. Despite becoming more aware and taking up more real estate within our brain, that perception of our hand and that awareness of that virtual image of our hand actually becomes fuzzier. So despite the increased area being dedicated to feeling that hand, we actually become less able to differentiate what we're feeling in that space. Because the only signals that we're actually being able to process and the only signals that are being increased are those of that nociception, that sensation that can possibly lead to pain. And because of that threat, anything we do with that hand is just sending that signal. So our awareness of where an injury might be or where the sensation might be actually shifts so that we're less aware of it. There's research to indicate that when someone enters a persistent pain state or neuroplastic changes create persistent pain, you can even just think about the affected area and it will become painful. Despite it not moving, despite it not changing, we can suddenly feel pain just by thinking about it, because that's what happens in our somatosensory cortex. We become aware of these different things, these different brain centers become worried and anxious, and we send that signal quickly because we're not sure if we're actually hurting ourselves. That fuzziness has made it more difficult to delineate whether or not it's being injured or if it's just a thought of being injured. Cool. So how do we get out of this state? How do we, quote, retrain the brain to become something else, to relearn how to move effectively without feeling these perceptions of pain, without experiencing these perceptions of pain? This rounds back to what we talked about last week, the 3 things that are very important for managing pain. First thing is sleep. As I discussed last week, sleep's very important for decreasing the central nervous system's engagement, that hyper-awareness, that hypervigilance of our bodies. It allows us to decrease latent stress hormone levels. It allows us to let the brain relax for a time, so we're not always fixated on the particular limb or the particular injury or the thought of that particular injury. Sleep should be an integral component of your whole process of recovery if you're feeling persistent pain for long periods of time. Doing things like taking medication or managing whatever way you can to make sleep more effective is a very important piece of this. Maybe that means turning off screens about an hour before bed. Maybe that means propping yourself up with as many pillows as you need to find yourself in a comfortable place. Whatever it might be, that's going to be an important piece of this process. Harnessing the neuroplastic components of our brain is important as well. This comes into that idea of stress management and mindfulness. Mindfulness feels like kind of a catch-call term. It's very trendy right now, but it is an important component of persistent pain management. If we're able to take our focus away from that constant worry about what our body is feeling, how we're experiencing pain, how we think it's going to affect us, if we can move our brain away from that space, if we can move our nervous system from feeling that to feeling something else or thinking about something else in a more effective way, we can use that neuroplastic principle, decrease the amount of space or real estate that pain has taken up in our brain, and allowing other pathways to become more effective once again. This will be one that I touch on a little bit later. We're going to do a little bit of a mental exercise if you want to keep listening in. Otherwise, continuing forward. The last thing that's important, discussed last week as well, is exercise in and of itself. Exercise sounds like a big, broad term. Usually it implies things like moving very actively, regimented regimes. Exercise can also just mean movement. Movement in a way that is understanding that we're actually not hurting ourselves as we move, despite the sensation that we're feeling, despite the perception of pain from that area. It is important that we move because it tells our brain that it is okay to move. And it decreases that neuroplastic change towards feeling pain. It allows you to disassociate that space and go, okay, I can actually move within this range. That's comfortable. It may be a little bit uncomfortable, but it's something that I can manage. And even that thought of, this is something that I can manage and this is something that I can change, is an important piece of that retraining process. So taking these three kind of components into account, we really need to find a way to sleep. We need to find a way to shift our thoughts and feelings away from that attention-grabbing pain process. And we also need to find a way to move as frequently and comfortably, or as frequently and almost uncomfortably as we can. Those three pieces will help begin retraining the brain. A quick review before we start this little mental exercise that I'm going to offer at the very end. Our body detects sensation through these receptors. The receptor information is conducted along neurons, those wiry little thin structures within nerves from the periphery to our central nervous system. The somatosensory cortex is a region in the brain where we have an internal image of our own bodies and how our virtual body feels things in response to different stimuli. Any of the information being collected from the periphery is still colored by our thoughts, our feelings, our emotions, and our experiences of that information. Neuroplasticity, the principle, is the ability for our brains to change and adapt to incoming information to become better or worse at processing it. This is useful in learning new skills, and remembering facts and things like that. With persistent pain, we get better. We learn how to better detect nociception, that threat of pain, and also we get better at interpreting sensations as pain. So it's a catch-22. We do both things. Neuroplasticity helps us, but it also can hinder us. Ultimately, what we need to do is try to figure out which ways we can retrain our bodies and retrain our nervous systems to recognize that every sensation we're having isn't pain. And we also have other sensations that come into our brains and come into our nervous systems that are as important or more important than that perception of pain. Sweet. Thanks, everybody. That's going to be concluding the kind of main components of the lecture. I'm going to lead right into a little bit of a mindfulness exercise. We're going to, wherever you are, if you want to listen in, feel free. If you don't, you can just sign out right now. It's going to be a body scan meditation or a mindfulness practice. This is a way to shift the framework from constantly thinking about a particular location and allowing the body to relax incrementally with awareness, which by extension allows us to shift the brain away from constantly feeling one area into understanding that the rest of the body is there too. And we allow it to relax and decrease that constant arousal and awareness of the rest of our body. So let's find a comfortable seat. Feel free wherever you are to sit down and close your eyes. And just take a gentle breath, finding a deep inhale and offering an exhale. Feeling the seat on your legs, feeling the clothes on your skin. offering yourself a gentle inhale breath as we collect awareness of our body. Offering an exhale, and just letting it go, letting it be as it may. Bringing our awareness around through our form, finding an inhale breath, feeling our feet maybe in contact with the ground. As you exhale, feeling them relax, feeling muscles soften, feeling our shins and calves relax. Skin to muscle, muscle to bone, everything settling down. Taking another breath here, collecting awareness of the knees, the thighs, the hips. Noticing as we exhale, muscles releasing, our body sinking gently into wherever we're seated. Noticing that gentle wave of breath filling through the core, up the back, across the chest. And as you exhale, feeling the spine gently stacking, core soft, breath gently flowing. Finding another breath, feeling it as it fills through the lungs, fills across the chest, the shoulders, the arms, and the hands. And as you exhale, letting the arms hang heavy, hands in lap, or wherever they may lay. Palms soft, fingers relaxing. Taking another breath, filling that space, filling the lungs, feeling the neck, awareness of the head and the face collecting. And as we exhale, feeling the neck gently settled, the head resting atop the spine, the face relaxing, the space between the eyebrows and the forehead softening. Noticing now, in a gentle, still space, our bodies calm. The mind stilling ever so slightly. If it flits, if it floats, if thoughts arise, finding a breath and letting them be with the exhale. Coming back to that grounding sensation. Finding your next inhale breath, recollecting awareness, feeling energy build within us, feeling our clothes on our skin, feeling the chair under our seat, bringing ourselves back. Awesome. Hopefully that was a little bit relaxing. That's just a simple mental exercise, what's called a body scan exercise or meditation. Something that takes no more than 5 minutes out of our day, but something that can help begin to retrain the brain and retrain that pathway, using that neuroplastic principle to pull us out of that constant state of mental or of perception of pain and bringing us back into living in our own bodies and as ourselves.